Okay. Good afternoon, everyone. Welcome to this webinar. It's my pleasure this afternoon to introduce my colleague, Paul Bartholomew, who's going to talk about his work on the ARCHER2 eCSE project, developing in-situ analysis capabilities for pre-exascale simulations with Xcompact3D.
Thank you very much, Claire. This was some work we did as part of the eCSE program funded by ARCHER2, and was with myself, Charles Moulinek, Michelle, and Sylvain Laizé from Imperial College was the PI for the project. So, to give a quick overview of the project, the idea was to make doing in-situ analysis easier for the Xcompact3D program. So I'll discuss further, but the basic idea of an in-situ analysis is that rather than your sort of typical workflow, which might look like the first half of the image on the right, where you run your simulation program, and periodically this performs some output, writing data to disk before proceeding with the rest of the simulation. And then once the simulation is completed, you load up an analysis program. So in our case, that's typically PowerView. This would then read this data from disk, perform some sort of analysis, and hopefully get the results required to answer the question that you've posed. The way that computer hardware is developed over time means that basically there's much more processing power than there is ability to write data to disk. So this becomes a bottleneck in terms of performance. The idea with an in-situ analysis is that you actually analyze the data your simulation is generating as it's being produced. And the effect is that you should get better performance because you no longer have to write so much data to disk. So the goal for this project basically was to make it easier for users to develop their own analyses for the Xcompact3D program without needing intimate knowledge of its inner workings. So a brief bit of background. Xcompact3D is a high-order CFD code built upon what are called high-order compact finite difference schemes, and these are used in combination with a spectral method for solving the pressure Poisson equation. And this combination of numerical techniques is chosen because it's very suitable for simulating the types of turbulent flows that users of Xcompact3D are interested in. So on the right, you see a visualization of one of the commonly used benchmarks for the solver, which is the Taylor Green vortex. As you can see, there's a very wide range of scales of flow going on, and these methods all very nicely capture these. Taylor Green vortex is at the simpler end of things that Xcompact3D is used for. So it goes from fundamental turbulent flows all the way up to one of the applications is simulating and optimizing wind farm layouts. So it's designed for use on high-performance computing systems such as ARCHER2 and parallelized using what's referred to as a two-dimensional pencil domain decomposition, which I've sketched at the bottom here. This divides your domain into a series of pencils along a given axis, and this means that you can apply your finite difference and your FFT operations along that axis. Obviously, I have three-dimensional problems, so to perform operations in the other axes, we have to transpose the data. This decomposition and associated communication is provided by a 2D comp and FFT library, which has been developed in parallel with Xcompact3D. And in addition to providing these parallel operations, also provides an interface to various FFT libraries and also parallel I/O, which is the focus really of this work. So originally this has been implemented in MPI I/O. Oops, sorry. Okay, unfortunately the text has gone a bit wrong here, but just to illustrate the issue that we're trying to address. So historically, solvers have received a lot of optimization attention. So Xcompact3D has been demonstrated running on up to order of 1 million MPI ranks on, I believe it was a Blue Gene computer somewhere. And on the right here, we can see some scaling data taken from ARCHER2. So for fairly large problem sizes up to 8 billion points, we're able to scale up to thousands of ARCHER2 nodes with pretty close to ideal scaling. And this scalability is also portable across different architectures. So here we have similar data taken from the ARM cluster Fulham at EPCC. So what I'm trying to point out here really is that due to the effort that's devoted to them, solvers aren't necessarily a problem in terms of being able to perform the kind of simulations that we want to. If we use more resources, we get expected speed up, and this enables us to do more science. At least that's the theory. Unfortunately, if we want to do science, we need to generate data in order to be able to answer the question that we've posed. So I've just repeated here roughly what the scientific workflow would look like. So as you're running your simulation, you would perform some output. You would take this output to analyze the results and answer some questions. Now, as I've just shown, Xcompact3D is a very scalable solver. So if we want to solve a question more quickly, we just use more computing power. Over on the right here, what I've shown is some data which is taken from, again, Fulham and ARCHER2, although it must be noted that the ARCHER2 data was actually on the pre-production system, so should be treated with a grain of salt. However, what we can see is here we're not just doing compute, but we're actually writing data to disk. And if we look at the Fulham results, then initially we do get speed up as we increase the number of CPUs being used. However, we very quickly saturate the I/O system, and even though our compute portion of our code continues scaling, the total time taken to run the simulation levels off, and this is due to the impact of I/O costs. So this can be a very sort of insidious cost to users who expect the code to keep on improving, resulting in wasted resources. And an additional challenge is that as we get access to ever larger systems, then the amount of data we generate grows alongside that. And so not only the cost of writing that data grows, but also the amount of storage volume required to keep it all starts becoming an issue. And then we also run into issues regarding managing that data. So, if we need to move it between systems, that becomes a significant cost. Just going to check. Okay, so hopefully after this slide, text will go back to normal. So as I mentioned at the start, the idea with in-situ analysis is to instead perform the analysis on the data before it's written to disk. And a way to think about this is typically you might only really want a single value out of your simulation. So on the right here we can see a simulation of a flow around a Formula 1 car using the Net++ solver. And this provides lots of detailed information about the flow field, which might be useful depending on what you're doing. However, you can also imagine that a designer of the car may simply be interested in the drag force, in which case writing out the entire three-dimensional flow field potentially very costly in terms of the amount of science they're able to do. So an in-situ analysis would perform the drag computation online, and then the amount of data that the simulation outputs is significantly reduced. And then down at the bottom here we see some data from Xcompact3D. So this is one of the diagnostic variables from the Taylor-Green vortex problem. this is recorded at very high frequency for checking the simulation, and if you're going to compute this after the fact from the full 3D flow fields, then the amount of data required would be totally impractical, and this really forces you to use in situ techniques. So what we want to do is find a way that we can make doing this easier for Xcompact3D users. So the idea is to avoid having to dig into the code base and edit it in order to achieve what they want. So the ARCHER2 framework has been developed by Oak Ridge National Laboratory for very large scale simulations. And their approach is to not only optimize I/O, but also make it runtime configurable. This allows doing many different things. So selecting, for example, between your file formats, or as shown in this architecture diagram, you can also use various plugins to perform all sorts of operations on your data, such as compression. But the particularly interesting thing for this project is because it captures the I/O process, it allows it to essentially redirect the I/O wherever it wants. So from the code's perspective, it might think that it's writing to disk, but ARCHER2 can step in and say, well, actually, we're going to write this to a network location. And you can also do the reverse, so you can have another program which wants to load data from disk, but ARCHER2 steps in and says, well, actually, we're going to receive from this network location. So this allows us to plug two programs together, so we can have a simulation that generates data and an analysis tool that's running concurrently, and they both exchange data via ARCHER2, enabling us to do our in-situ analysis. So the first part of the project was to integrate ARCHER2 into Xcompact3D. The 2D comp and FFT library already had a existing MPI I/O solution for doing parallel I/O at large scale. We wanted users to still be able to use this as part of their workflows, so ARCHER2 was added as an optional backend, which could be selected at compile time using these preprocessor macros. The good thing about this was it meant that the vast majority of changes to the code are invisible to the user. However, this use of preprocessor macros with hindsight was a bit clunky, so there's some ongoing work to correct that, which I'll discuss later. But by and large, the only changes that users would notice is that they now have to declare upfront what data they want to write out, because this is required by ARCHER2. So in the MPIO backend, this is just a immediate return type operation. We also have to work with some slightly different concepts. So Xcompact3D writes often a file per field per time step, whereas ARCHER2, part of its goals is achieving high performance I/O, and it does this by buffering up I/O operations. So rather than synchronously writing immediately, you'll start doing an I/O, and it won't necessarily complete until you close the file. And then, so if you've got, for example, 4 or 5 fields that you want to write, in theory, these should all be pushed much more efficiently than sort of opening, pushing, closing, opening, and so on. So there was a bit of work in the back end required to work around that and support both the original approach and the new one for ARCHER2, but otherwise it's fairly straightforward. And on the right here, you can see how you can configure the I/O at runtime. So you have these various handles to different engine objects, and basically declare what format you want. So for example, here I've used HTF5, and you can configure some options within the HTF5 library on this. So with ARCHER2 integrated into Xcompact3D. We ran some benchmarks on ARCHER2 to see how the performance compared against the existing MPIO backend. So I'm afraid the figure's a bit small, but on the left, what we're looking at is the effect of different backends within ADIOS2 and MPIO and changing the striping on the Lustre system. So the green graph shows HDF5 effects, the HDF5 backend, and as you can see, I had a very hard time achieving any reasonable performance and also consistent performance with this. I noticed when putting this presentation together that I'd copied some collective options from the ADIOS2 documentation, and a PhD student here at APCC who's also been looking at ADIOS2 has found that using collective I/O within the HDF5 backend significantly slows things down. So if I was to revisit this, I might get better performance with HDF5. The orange and the purple lines show the MPIO backend before and after we'd made any changes to 2D comp and FFT. So this shows that we get consistent performance and haven't really affected things too badly. The other thing you can see is as we increase the number of stripes, so that's the lines traveling down the way, the performance increases, and this is what you'd expect because the stripes is basically how many parallel consumers you have in the hard drives. And then finally, this pale blue line is ADIOS2, and basically it scales very well. So it starts off slower, but by the time we get up to 16 nodes on ARCHER2, it's outperforming the MPIO backend. And this is because ADIOS2 takes a file per node type approach rather than a single file, and so this scales very well as you increase your simulation size. The second figure is look at the bandwidth we've achieved. So this is concentrating just on the ADIOS2 backends because I've given up on HDF5 at this point and MPIO. So we struggled to get very good performance really out of the MPIO backend, whereas ADIOS2 out of the box was working very well. And the nice thing also, which we benefited from here, was by using the ADIOS2 library, we also gain from any improvements they make. So when I started this project, we had the BP4 backend. At some point, they introduced BP5. As you can see, this is achieving up to 1,024 nodes, around about 100 gigabytes per second, which is near the theoretical limit for the the ARCHER2 backends. So that was pretty pleasing to see that effect. So that's without having to change really much about their workflow, that's an immediate benefit for users of Xcompact3D. Okay, unfortunately we're back to dodgy text. So the second part of this project was to integrate the Python Compact3D framework into an in-situ approach. So Python Compact3D started between me and another postdoc to bring together some post-processing scripts we developed independently. We realized there was a lot of overlap, so we developed this sort of single library that we could use to share any new analysis tools. So it's based on NumPy, and the idea was to make it easier to load data from Xcompact3D outputs, both diagnostic files and 3D data sets, and also to facilitate analysis of that using the same numerical schemes in Xcompact3D. So what you can see here is how you'd write a derivative in the Xcompact3D framework. This ends up in a large tridiagonal system to solve. It's obviously very slow in Python, but using NumPy, we thought we'd get reasonable performance. And this was generally focused on workstation use, so was entirely serial in implementation. So if we're going to use this as part of a workflow on a supercomputer like ARCHER2, obviously it needs to be parallelized. As it's based on the same numerical schemes as Xcompact3D, then logically the same parallelization strategy should work. where we use this pencil approach from 2decomp and FFT in order to decompose the domain and compute things in parallel. So to do this, I used the F2Py tool to write a Python binding to the 2decomp and FFT library, and this allowed me to take the serial code and parallelize it using MPI and begin running things at scale. So as a test, I computed the gradient of a field on ARCHER2 on a range of mesh sizes, and given that there's sufficient work to keep the processors busy, then get good scaling up to 2048 cores. One thing about Pi for Xcompact3D is that it was intended to be easy to use. So in terms of the layout of data, it's always in what we refer to as the X orientation. And this means that when doing computations in parallel, we keep on moving data back to X. This is a trade-off between ease of use and performance, because this will obviously add additional communications overheads, which may be something to consider in the future. So with Pi for Xcompact3D running in parallel, then the remaining step to enable these in-situ analysis was to integrate ARCHER2. So rather than loading binary data via NumPy, using the ARCHER2 Python interface, Pi for Xcompact3D could read the data being output by Xcompact3D when it uses the ARCHER2. And this is where the runtime configuration is very nice, because you can start off with a traditional approach where you'd say write a HDF5 file in your simulation, and I can test that Pi for Xcompact3D reads this correctly via ARCHER2 and check that all the computations are correct. So on the right here, we see a figure which I showed earlier, and what this is comparing is that the diagnostic data being computed by Xcompact3D and Pi for Xcompact3D are consistent, which is what you'd expect given that we're using the same numerical methods. So once I was happy that was working, then all you have to do is at runtime change the output type from being a file such as HDF5 to what ARCHER2 calls SST, which is a streaming transport layer, and this now starts using a network interface to write and read data from. There was a problem in the ARCHER2 interface because it's very high level in the way that it's written for Python, and it wants you to kind of write this range-based loop, which didn't fit exactly how we'd develop Pi for Xcompact3D. So I needed to dig into the iterator that it exposes and start using that, but it's not really ideal because in theory it could change, but given it's the way that Python loops seem to work, I think that this is likely to remain stable. As I said, this matches the data generated by Xcompact3D directly, so it all appears to be working well. But the issue I ran into with this was that if Xcompact3D runs faster than Pi for Xcompact3D, even though both are parallel, eventually you get these out-of-memory errors as the data as the unprocessed data begins to accumulate. So the way to address this obviously was to look into optimizing Pi for Xcompact3D. As I said earlier, we've implemented these tridiagonal solvers using NumPy. It's operating on a large 3D problem, but there's a loop carried dependency across one of the axes within that. So this outer loop was written in Python with the expectation that the inner two loops being expressed as NumPy operations would mean it's fast enough. Evidently, this was not correct. NumPy, however, can't express this loop carried dependency, so an alternative approach was required to rewrite this in pure NumPy to get the speed that we need. So if you're familiar with tridiagonal solvers, essentially they can be written as a recurrence relation as shown here, and luckily this has a closed form solution, which there is a reference, but it's all obscured by the text. Which looks like this, and basically what this is a series of matrix and vector operations, which is the kind of working data types for NumPy linear algebra module. And by writing it like this, Python Xcompact3D was then able to keep pace with the Xcompact3D rate of data generation. So finally, with all this put together, what we did was we ran the Xcompact3D problem on ARCHER2 with Python Xcompact3D running at the same time, and we sent the data from Python Xcompact3D to Python Xcompact3D via ARCHER2, and we tested this on a range of problem sizes, on a range of core counts, and compared the speed of Xcompact3D running by itself and the coupled Xcompact3D Python Xcompact3D case. And so what you see on the right is the timings that we achieved. Basically, a consistent picture that emerged from this is that there was no appreciable slowdown until Xcompact3D was running on more than 4 times as many cores as Python Xcompact3D, after which you began to notice a significant drop-off in performance. However, at this point, Xcompact3D was already approaching the limit of its scaling for these problem sizes, so there's no appreciable impact for reasonable amounts of resources being used using this external in-situ analysis framework we've developed. So to conclude, we've now got an optional ARCHER2 backend added to Xcompact3D, or technically the 2D-comp and FFT library, which means that other codes that build upon that can also make use of it. Adding this ARCHER2 backend gives an immediate performance benefit for users in their I/O. The Python Xcompact3D toolbox has now been parallelized for use on HPC machines, and we've been able to demonstrate in-situ analysis running on ARCHER2 at realistic scales and realistic problem sizes. In addition to this, there's a new release of 2D-comp and FFT, which has been published in the Journal of Open Source Software, and this includes the ARCHER2 backend. There's an improved object-oriented I/O interface being developed in 2D-comp and FFT, and this makes the interface between selecting MPI and ARCHER2 much cleaner than the original approach of using compiler macros. So if you do use 2D-comp and FFT, this should make things much easier for you to work with. Some further work that we still have to do is look at ARCHER2's file compression plugins. So a very quick test showed that these gave us a 25% reduction in file size, so that certainly looks like a very interesting thing to look at further. And also enabling visualization using PowerView and Catalyst was something that was attempted but not able to complete in time. And finally, references if you'd like to know more about Xcompact3D, 2D-comp, or more about this eCSE project, and GitHub links for the software involved are also available here. So thank you very much for listening, and happy to answer any questions.
Thanks very much, Paul. Some questions in the chat there.
Yeah. So Alexei's asked, are there any plans to move data processing to a GPU or the CPU if the main simulation uses GPUs and around heterogeneous architectures? That's been considered. So there was a Gordon Bell prize submission for a code called Neko, which used an approach like that, and I think they were can't remember how they were doing it, but we certainly considered submitting an eCSE project based around using ARCHER2 to achieve that kind of offloading approach. But at the moment, the analysis only runs on the CPU, and there's work in progress to get Xcompact3D or a new version of it running on GPUs. So yes, certainly something interesting, but nothing concrete has been done yet. And Sebastian has asked, for the in-situ analysis, do the locations of the X3D and P3D, or Xcompact3D and Python Compact3D ranks matter? Does having them on the same node make things better? So I think it would. However, what I didn't mention was because of the way that the Slurm submissions worked, or at least the way that I'd written them, you had to run one node for Xcompact3D, or on a given node, you'd be running either Xcompact3D or Python Compact3D. So there was inherently some network communication there. Certainly, if you could put them both on the same node, I think that would be beneficial. But that would be something further to investigate.
Thanks for that. Any further questions? Okay. I'd like to thank Paul very much for that presentation, and for everyone that came along this afternoon. Thanks very much, and bye for now.
Thanks, everyone.